Good morning, everybody. Hopefully, most of you know who I am. My name is David Wavell. I'm the Business Development Lead for the ORCA Hub project. So welcome to the third of our challenge information sessions that we've been holding this week. Just before we get started, I just want to let you know that we are recording these sessions. They're going to be posted on our website, social media and YouTube channel. So if this makes you uncomfortable for whatever reason, then please take whatever action you think is necessary. So just before we get started today, I just wanted to go over the purpose of these events, which is to provide you with more information about the challenges that we have set out to solve in the extension of the ORCA Hub. Hopefully you managed to attend the webinar on the 17th of June and got a flavour for what we've achieved so far and what we're planning to do next across the whole of the Hub. This morning, you're going to hear from Dr Ioannis Havoutis about one of the ORCA Hub's lead academics, about how he and his team will work on robust robot inspection and manipulation in hazardous environments. So Ioannis will present his work for about 20 minutes. We'll then open the floor to a few questions at the end. Please add your questions in the chat throughout the presentation, and we will address as many of them as we can. If we don't manage to get to them before the end of the time, then we will address them afterwards in a follow-up email. So just before I hand over to Ioannis, following the events this week, we're going to be hosting a series of AIM days in the first 2 weeks of August. So we'll have one for each challenge. The purpose of these AIM days is to give you an opportunity to speak one-to-one with the academics leading the work that we've discussed this week, so that we can discuss working on projects together related to their challenge. So if after hearing today's session, you're interested in discussing a project idea you might have, please get in touch with me at my email, which I'll put in the chat function shortly. And I'll send you a pro forma to complete outlining your idea. This will then give us a bit of pre-read information that we can use to help plan and prepare for the AIM day with you. You can see the times and dates for the AIM days on the slide here. We will also post these in the chat shortly. They'll also be available on our website and our social media channels with more details about how to get involved. So enough from me. I'm now going to stop sharing my screen and I'm going to hand over to Ioannis for his presentation. So over to you, Ioannis.
Good morning, everyone. Thanks so much, David, for introduction. Let me start sharing my screen. And I hope you can now see the title of my slide deck.
Yes, we can do that.
Awesome, great. All right. So welcome to the presentation of Challenge 3. I'm Ioannis Havoutis. I'm with the Oxford Robotics Institute, and I will tell you a bit more about the third challenge of the current work of the ORCA Hub. So this is the challenge on robust inspection and manipulation in hazardous environments. And next slide. And of course, this challenge combines four main research directions that the main aim of which is to automate inspection and maintenance solutions for large multi-floor facilities. So in many cases, this is really dependent on having non-wheeled mobility in cluttered spaces with sensing and manipulation payloads. And I'm going to get to a bit more detail on that in the following slides. But another thing that is coming up in our current work is that both navigation and physical manipulation are central to this challenge. And of course, much of the work currently is geared towards that, is geared towards manipulation, and will on one side take the form of non-destructive evaluation, so how to do inspection, for example, with image electromagnetic transducers to do inspection. And of course, more general interaction with the facilities, such as turning valves, pressing buttons, operating circuit breakers, opening hatches, doors, and so on. And last, one of the main new areas of research that we will be working on is developing automated solutions for gas cutting. And I'll also get to a little bit more detail on that in a few minutes as well. So here are the platforms that we will be focusing on for this work. So we're mainly focusing on quadrupedal platforms, as mobility is essential for the task that we are focusing on. We will have a range of platforms. The ones that are shown here are mainly the ones that we have been working on and are planning to do deployments on. So you will have the animal B with a manipulator mounted on top that is available both at the University of Edinburgh and here in Oxford. And then we have another set of platforms that are more geared towards navigation, mapping, and inspection, such as the Animal C robot on the right and the Boston Dynamics Spot robot in the middle. Of course, we'll be taking some of our control work on animals and other platforms as well. But what I also want to highlight is that much of our work is equally applicable to platforms that are wheeled or tracked, for example. So our work on mapping and SLAM and inspection can equally be applied to other forms of mobility. All right, so the challenge builds on our strengths, of course, from our previous ORCA Hub work. And the main focus now is further developing our inspection and manipulation capabilities. I hope many of you have already seen some of the deployments and demonstrations that we've done over the past 3 years as part of the ORCA industry demos. But now what we're focusing on is these 4 main tasks for the challenge. So one would be, of course, navigation and manipulation for real-world facilities, working more towards inspection and intervention capabilities, automated monitoring of the state of a system, doing all that with online perception feedback, which would be important for the leftmost task that we'll be working on with the animal robots, with the manipulators. And then the second task would be on developing scanning capabilities to deal with complex curved surfaces and how to best integrate that with Loco-Manipulation capabilities with our platforms. As a third task, of course, this is extending our autonomy framework to work with the Spot robots, and we are aiming at developing more capabilities there on the side of anomaly detection that we can deploy both on animals and Spot robots. And the rightmost task would be on building a gas cutting site mockup and develop close contact manipulation tasks that target waste disposal and decommissioning of large irregular structures. And all these tasks are mainly supported by the ORCA partners listed there, the University of Oxford, Watt Imperial, and of course, the University of Edinburgh. All of us have already a strong track record along the lines of the tasks that we're proposing here. And we hope that we can develop and extend this quite a bit over the course of the next year. So now I'm gonna go in a bit more detail on each of the strands of the challenge. I realize that I have way too many slides here, so I'm gonna be quite brief on each slide. But I think it's quite important to have this information here so you can go back to that, or you can ask more questions and go into more detail into the particular aspects of the project that you're more interested in. So first of all, on navigation and manipulation in cluttered environments, we've been already working on facility level multi-floor path planning. And now our focus would be on how we can add temporal semantic information and how to integrate that into a digital twin of a facility. And these are some examples of how the work will be shaped. So this is the approach that we have developed over the past 3 years on working with the ORCA Hub. So this is a geometric-based approach that can either use point clouds that we collect on site with the robots, or we can use a model of the facility that we had beforehand. And this we've developed a geometric approach that builds a digital twin of the facility, and this can then be used as on one hand as a way of doing really fast motion planning or route planning on multiple floors, and on the other hand as a way of storing other aspects of the facility as temporal information, semantic information, occupancy information, and any other type of detail that we want to be able to log. So this is how this looks from the perspective of the robot, and this is what we use to do the path planning. But what I think is more interesting is that this is what enables us to be able to react online to a changing environment. So, for example, having a robot that does inspection tasks completely autonomously, and then having different routes change, for example, having obstacles or people in the way of the robot, and having the robot autonomously decide which path to choose or how to avoid moving obstacles and how to deal with humans and so on. And of course, this is only one part of the bigger picture. That is the capabilities that we've been developing for completely autonomous inspection of large industrial facilities. Here is one clip that some of you might have already seen. This is the framework that we developed for building a map and then having a robot perform this sort of inspection tasks in a completely automated fashion. So the robot here is following a route that is its regular inspection path, and then it's pointing its sensors to the points of interest that we have pinpointed on the map. And this is a task that can be performed autonomously and over a temporarily extended period of time, so you can get very precise data from the facility, and you can have a clear picture of how these evolve over time, over long periods of deployment as well. So you can, apart from dials, for example, and valve states and switch states and so on, now we will be integrating other information as, for example, heat signatures, anomaly detection, corrosion detection, structural deformation, and so on. And yeah, this is a bit more detail on what I briefly touched upon earlier. So this is how we can have a robot navigate a facility. Here the facility is our lab space and our office space in Oxford, and then understand in a sense what parts of the facility belong to which room, or through a set of geometric and semantic processing boxes, if you want, then understand, for example, which parts of the facility are corridors, staircases, doorways, or more detailed temporal information, like this part of the facility, for example, during the day is generally slippery or wet, And this part of the facility, for example, at that point during the day is more crowded. So, for example, on building a path through the facility, this is to be avoided and so on. And of course, this is part of the work that we're developing to support manipulation on these platforms. Here you can see an example, a work that the University of Edinburgh has developed. So this is how the main point of this work is how to work on real-world environments. Here's a lab demonstration and how to adjust, how the robot can autonomously adjust to a set of challenges that might or might not be observed by the robot. These are very extreme cases that you see here, both in a physically realistic simulation and the real system examples. But this is kind of demonstrating the robustness that we require of the systems that need to perform these sort of tasks in a real-world environment. And of course, this is another main point that we're bringing up here for the manipulation capabilities, that this would be using real online sensing to be able to perform these complex tasks. This would take the form of a number of demonstrators on facilities of partners and of course in lab. And what we're aiming on having here as a result is automating many loco-manipulation tasks that are either performed autonomously by the robot. I mean, the tasks are performed autonomously by the robot, but they can also support search control with a teleoperator, for example, that might be commanding the robot remotely, or completely autonomous operations in an energy facility where the robot needs, for example, to turn valves, switch, toggle switches, open doors. So this can be part of the regular route of the robot, or if the operator is commanding the robot to reach a particular point, then there is an interface that is very intuitive to work with, where you can command the robot to perform particular tasks that are done autonomously. So, of course, much of this work is underpinned by our mapping and map building framework. Let me see why this video is not already playing. All right, here we go. So this is what allows us to build very accurate models of facilities. Here is building a model of a college here in Oxford. So a set of buildings, a number of passageways, large areas. So a combination of many different areas and areas with different characteristics. And of course, this can be deployed in various platforms apart from the legged robots that are shown here. Also on wheeled vehicles that we have experimented with. And much of this pipeline is supported by sensor payloads that we have built in-house and have been using successfully over the past years for very accurate mapping and localization. So this is more recent work on that front. So this is integrating our sensor payloads on a spot robot and having the spot robot navigate our office space and our lab space, and building a very accurate digital twin of our building. And you can see a number of capabilities that we have here. Of course, the mobility of the platform is very important here. So many tight corridors, narrow passages, going through doors and so on, and building a very high fidelity model of the environment, at which these are multiple floors that we're showing here, and where we can very accurately localize and then, of course, build on top the information that we want the digital twin to contain. Moving on to close contact inspection with image sensors. So we have already demonstrated in our previous ORCA work how we can use these NDE sensors to inspect areas of interest or pieces of interest. We have shown how we can perform these scans autonomously. So here is one of the mobile manipulators that we have worked with as part of ORCA, and here the system is scanning a flat surface to inspect the sound, to inspect the thickness of the material. This is a capability that we already demonstrated, and what we want to extend that to in our current work is, of course, more complex structure, so curved components, and we are looking into integrating this with Loco-Manipulation capabilities with our Quadruped, so we are more flexible on the surfaces that we can approach and we can evaluate. So integrate onto more platforms and then extend capabilities to more complex surfaces and more complex geometries. So for example, examining weld points and where pipes meet pressure vessels and so on. More interesting tasks and more challenging structures. And last but not least, the new area that we will be exploring, the smart tool wielding for decommissioning and waste recycling. This is of course leveraging the autonomous manipulation capabilities that we are building with the other platforms. This will initially have the form of a gas cutting mockup in a controlled setting in the lab, because we are not that familiar with the machinery yet. But through our work and through having a better understanding of how these need to be regulated, or how the contact with the piece that we're operating on needs to be handled by the robot, then we're looking into integrated that into mobile manipulation, be that at a smaller scale on Quadruped, or a specialized robot that is tasked with gas cutting tasks. And of course, this is with a view towards decommissioning of larger structures, be that CPALs and large metal structures with the irregular geometries.
Thank you, Ioannis. Thank you very much. So yes, we have a couple of minutes for questions. Ioannis, if I could just ask you to stop sharing your screen, and I'll put mine back up with information about the aim days and things. So we had one question regarding the explosion proofness, if that's a word, of the robots. Is it in scope to look at the certification and hazardous use of the robots?
Yeah. So the quadrupeds are not, for example, latex specified, and this would be a long process to achieve that. On the research side, this is not something that is this is something that we will be happy to support, but this is not something that we will do ourselves. So the manufacturers of the robot are most likely the ones that would go for the ATEX specification, for example, and we'd be happy to support that. We already have some ideas about how we can do that. So we have been looking into, for example, gas sensors that can be integrated on the robots, so their gas exposure safe. So when gas is detected, robot shuts off, and this is one of the ways to mitigate explosion risk.
Okay, thank you. So I don't see any other questions in the chat, but I've got one which I'll just ask, which you did briefly cover in the last slide there. So given that we're an industry-driven program, what are the key things that you'd be looking for support from industry for your scope of work?
We're looking for use cases that are hard and exciting for industry. So let us know about your problems, and we will try to solve them with the technology that we're developing.
Lovely, thank you. So that actually is quite well timed. It takes us to 10 o'clock. So thank you very much, everyone who attended. Thank you very much to Ioannis for presenting today. Just to remind everybody that we have the AIM days coming up in the start of August. So Ioannis's AIM day is on the Friday, the 6th of August, from 9:30. So if you're interested in getting involved in that, please drop me a note. My email's in the chat there, and we'll take it from there. So on that note, thank you very much again, everybody, and hopefully we'll see you all for tomorrow's session.
Thank you very much, everybody.
Bye-bye.